Okay, this is quiz 4 for physics 201, fall 13. First, consider a child who is swinging. As she reaches the lowest point in her swing, which of these is true? Well, first of all, I have this, child swinging back and forth, going back and forth and back and forth. And at the lowest point, I have a couple forces acting on it. I have the tension in the string, Ft, and then I also have the weight, Fw. And so at that bottom, I can write these things. At the lowest point, I can say that Ft minus Fw equals mv squared over r, right? Because that's her ma, her mass times acceleration. And so let's see, most of these are about the tension, so let's just solve this for tension. Is equal to Fw plus mv squared over r. So that means that the tension is going to equal the weight plus this mass times the centripetal acceleration. So the tension is going to be bigger than the weight, which is A, or excuse me, which is B. It's not less than the weight, it's greater than the weight. The tension is not equal to the centripetal force. The tension minus the weight equals the centripetal force, and the tension does not equal the mass times the acceleration. All right, a rigid body is rotating with a negative omega. Now, let's imagine this is my rigid body. A negative omega would mean it would be going in this direction. It's a negative omega. It's speeding up in its rotation. That means that the angular acceleration is in the same direction. So it's also negative, or it is clockwise. A disk is rotating at 3 revolutions per second. What is it in degrees per second? So 3 revolutions per second. In 1 revolution, there are 360 degrees. So let's see, that's 900 plus 180. It's 1080. Or just keeping 1 sig fig is going to be 1,000 degrees per second. When traveling around a banked curve, which of these forces provides the centripetal force? All right, we have 2 forces that provide the centripetal force. I won't draw the whole vector diagram here, but we have components of the normal force in the x direction and a component of the static friction in the x direction. This is sort of like the horses when they ran around the circle. They were banked, and so the floor was pushing back on them. In a similar way, not only does the static friction hold your car on a banked curve, but also the normal force. So let's see, that's 2 and 4. That's D. Number 5, consider a point on a spinning wheel with alpha equal 0. That means that it is not accelerating. Which of these means the angular acceleration is 0? Which of these describes the linear velocity at the point? The linear velocity is the same as the angular velocity? Okay, no. The linear velocity is changing constantly. That is true because linear velocity is a vector quantity, and now the magnitude is constant, but the direction is changing. So because that direction is constantly changing, the linear velocity is constantly changing. Let's see, what is the moment of inertia for this system? I have a sum of mr squared. That's going to be 1 kilogram times 1 meter squared. There are 2 of those, so I'm just going to multiply that by 2, plus 4 kilograms times 2 meters squared. Now let's see, that's 2 times 1, that's 2, plus 16, that's 18 kilogram meters squared. This figure, 3 levers of the same length, each holds up a block of mass m. List the 3 levers in order of the force required to hold up the block, from the greatest force required over here to the least force. Now the greatest force is this one, which has the shortest moment arm here. The least force is this one. So the greatest is going to be 2. The least, or excuse me, this will be the greatest. The least is number 3. Excuse me. Yeah, that's right, 3. And then the middle one is number 1. So it should be 2, 1, 3 is the answer. B. Number 2 first, number 1 second, and number 3 third. I might change that to A, B, C, so a little less clear. Or a little more clear, excuse me. Which of the following systems is not in rotational equilibrium? All right, rotational equilibrium means that the sum of the torques will equal 0, and also because of that, the angular acceleration will equal 0. Figure skater spinning faster and faster on ice. That is not in rotational equilibrium. It has an angular acceleration greater than 0. Ball spinning in place at a constant angular velocity. All right, that one is in equilibrium. Constant angular velocity means that alpha equals 0. Let's just look at these. Or excuse me, no, is not in rotational equilibrium, so it's not that one, and it's not that one. It is A. A is not, sorry, if it's not in equilibrium, alpha is greater than 0, okay? And so that's going to be option A. Let me fix that here. Here I have a figure skater spinning faster and faster, and alpha is greater than 0. For all these others, alpha is equal to 0. What are the units for moment of inertia? Well, the equation is mr squared, so that's kilogram meter squared, B. And then finally, which of these experiences the greatest torque, and which of these has the least torque? Well, the greatest torque is going to be the one that's most perpendicular, or that's closest to perpendicular and at the largest moment arm. That is going to be number 3. That one has the greatest torque. So that gets rid of B and D. And now it's either between 2 and 4. 2 and 4 appear to have equal angles here. So those forces aren't perpendicular to the moment arm, which would be ideal. That would give you a larger torque. But number 4 has a much smaller moment arm. Remember, torque is Fr sine theta. So if R is small, theta and F are the same, then the torque will be small. So number 3 is the biggest, number 4 is the smallest. So 3, that's going to be A for number 10. Okay, merry-go-round rotates from rest with an angular acceleration of 1.5 radians per second squared. How long does it take to go through the first 2 revolutions? All right, so first of all, let's just write down what I know. I know that omega naught equals 0, alpha equals 1.5, and theta equals 2 revolutions, which is, that's 2 times 2 pi. Let's go and convert this. 1 revolution, 2 pi radians. That's going to be 4 pi radians. And I want to just know how much time. Now let's just write down our equations. I have omega equals omega naught plus alpha t. And I have theta equals omega naught t plus 1/2 alpha t squared. This one's pretty simple because I'm looking for t. And I have these quantities, so clearly I need to use this. Now, omega naught goes to 0, so that whole term goes to 0. So I get 4 pi, which is theta, equals 1/2 times alpha, which is 1.50, times t squared. And then if I solve for t, 8 pi, divide by 1/2, and then 4 pi becomes 8 pi, 1.50. I get 4.1 seconds. Okay, now the second part, right here, I want you to show me how to find the time for the merry-go-round to move through the next 2 revolutions. Looks like I've run out of space, but I'll give y'all more space on the exam. So I'm going to try to squeeze it in down here. To move through the next 2 revolutions, what do? Well, I need to do this. I know that omega final is omega naught plus alpha t, and I also know that theta equals omega naught t plus 1/2 alpha t squared. Now, I need to find omega final at 4.1 seconds, so that's going to be 0 plus 1.5 radians per second squared times 4.1, and that's going to be 1.5 times 4.1. That's going to be 6.15. radians per second. Now, this is going to become the omega naught that is in this equation. And it looks like this. I'm looking for the rotation through the next two revolutions. I know that's a theta of 4 pi equals 6.15 times t plus 1/2 of alpha times t squared. And then you solve that equation. I don't require you to solve it. That requires the quadratic formula. And as I told you in class, you just set up the quadratic and just leave it at that. Okay, so that's what I was looking for. All right, consider these masses on a rod rotating about the fulcrum. The rod's 4 meters, has a mass 3 kilograms. What's the initial angular acceleration of the system? Okay, so I have a couple different things here. First, just let's list the forces. So I have a force here. That's the force weight, which is 2 times g. I'll call that 20 newtons. And here I have a force equal to 10 newtons. And I want to know what is alpha equal to. The sum of the torques equals I times alpha. I can sum up the torques here. If I call this torque 1, I call this torque 2. The sum of the torques will equal, let's see, torque 1 is counterclockwise, so it's positive. Torque 2 is clockwise, so it's negative. That's going to be 20 newtons times 2 meters minus 10 newtons times 2 meters. That's 40 minus 20, which is 20 newton meters. So that's my net torque. Then, if I want to find my alpha, I also need to know I. Now I is going to have 3 components. I have 2 discrete particles and I have a bar. So it's going to equal mr squared for one of the components, one of those particles, plus mr squared for the other particle, plus 1/12 mb squared. That's for the rod. So that's going to be 2 kilograms times 2 meters squared plus 1 kilogram times 2 meters squared plus 1, that should be a 12th, 1/12. The mass of the rod, which was what? 3 kilograms times 4 meters squared. Let's see, that's equal to 8 plus 4. 1/12 of 16, that's 4 over 3, plus 4. That's equal to 16 kilogram meters squared. So now I have I, and I have alpha, and I have sum of the torques. So I find alpha, which is the sum of the torques over I, which is going to be 20 newton meters, divided by 16 kilogram meters squared, which will give me, what's that, 5 over 4, 1.25 radians per second squared. Collection of particles rotate around the axis as shown. A force of 3 newtons is applied to the 4 kilogram mass. Force is applied perpendicular to the rod that the mass is attached to. What is the angular speed of the system after 2 seconds? All right, the angular, first of all, I need to find the moment of inertia. And then I have a force that's applied. So I can find the torque. This is similar to what we had before. And then I want to find the angular speed. So first of all, let's just find the moment of inertia. In fact, this was a multiple choice question. So I've already found that. It was 1 plus 1 plus 16. It was 18 kilogram meters squared. All right, so that's my moment of inertia. You can look back in the multiple choice, see the solution. My net torque, there's just one force. It's acting on this particle. Excuse me. It's acting on that particle perpendicular. So it's like it's coming out of the page. The force is coming out of the page, pushing on that particle. And let's see, what was that force? Is applied 3 newtons. So the net torque is 3 newtons at 2 meters. So the net torque is 6 newton meters. I want to know alpha. sum of the torques equals I alpha. So alpha is the sum of the torques over I, which is going to be 6 over 18. 1 over 3. Right, so that's in radians per second squared. Now I want to know what is the angular speed of the system after 2 seconds. So almost done. So I say omega equals omega naught plus alpha t. That's going to be 1/3 radians per second squared times 2 seconds, which will be 2/3 radians per second, or 0.67 would also be appropriate, or 0.7 even. Now I also want to know what is the linear speed. I know that v is equal to omega times r. I want to know the linear speed of one of these 1 kilogram masses. It's at a radius of 1 meter. So I just say 2/3 radians per second times 1 meter, which is 2/3 meters per second. That was part B. That was part A. Now, finally, let's see. Boy swings a 2 kilogram stone in a vertical circle. The radius is 2 meters. The string breaks when the stone rotates at 2 radians per second. What tension in the string will cause it to break? Where in the circular path does the string break? I know that my tension is largest at the bottom. We've already sort of seen that with the kid on the swing. Let's just redraw that. So I have this ball. I have forces acting upon it. I have the weight of the ball, and then I also have the tension in the string. And I know that the sum of the forces equals Ft minus Fw, and that's equal to the mass times the acceleration, which is v squared over r. And so I want to know what is the tension. The tension equals mv squared over r plus the weight. And so let's see, I have some things here. Looks like I don't have v, instead I have omega. Omega equals 2 radians per second. Mass equals 2 kilograms. And the radius is 2 meters. You could do two things here. I'll do it this way. I'll just say v is equal to omega r, and find v to plug into our this. That's going to be 2 times 2, which is 4 meters per second. So that's my linear velocity of this ball as it goes around at this constant angular speed. And so put these values in. I have 2 kilograms times 4 meters per second squared over the radius, which is 2 meters, plus the weight of the object, which is going to be 2 kilograms times 10. That's going to be 20 newtons. That's 32 over 2, which is 16 plus 20, 36 newtons. So that's the tension in the string that causes it to break. I just want to note it does break when the stone rotates at 2 radians per second, and that's the tension that will cause the string to break then, 36 newtons. Just realize that there is no cross product on, so I'm going to go back and edit this a little bit, but it'll be largely the same. I might take out one of these parts, or maybe even remove one of these questions altogether. But let me just go ahead and show you a cross product here in the end. It'll just be a simple cross product. I'll just do one here. Let's say that my force is, I don't know, 2I newtons minus 1J. And let's say that this acts at a moment arm equal to 3I minus 2J meters. And I want to know what is the torque. The torque is R cross F. In fact, I'll use these numbers, so you'll see another question here. That's going to be 3I minus 2J crossed with 2I minus 1J. It's very important that you get the order in the cross product, because remember, R cross F is not equal to F cross R. It's equal to the negative of F cross R. I know that I cross I is equal to 0, so my first terms, that equals 0, because I cross I and J cross J are both equal to 0. So my first will give me 0. My outer That's going to be 3 times negative 1. That's going to be negative 3 times I cross j. The inner will be negative 4 times j cross I. And then the outer will be 0, because j cross j equals 0. Now I need to know what is I cross j and what is j cross I. You can use your right-hand rule. You probably know this, but if this is I, j, k, I cross j, I let my fingers go in this direction. They fold towards the j direction, and then my thumb of my right hand points in the k direction, the positive k. So it's going to be negative 3k. And then j cross I is just the negative of that, so that's going to be plus 4k. So my net torque is going to be plus 1 k Newton meters. That's 1 Newton meter in the positive z direction, or out of the page in this case. So as I said, you'll have a problem like that.